Okay, so we're starting with an invited talk of about 35 minutes, including questions. The title of the talk is How to Increase the Accuracy of Human Forecasts and Check the Reasons for Improvement. So we have two speakers sharing the talk, which is really exciting. We have Barbara Mellers. So Barbara is the George I. Hayman University professor at the University of Pennsylvania in the School of Arts and Sciences and the Wharton School. A cognitive psychologist, she studies how and why people form beliefs, judgments, and preferences, and she's the co-PI of the Good Judgment Project. Ville Satopa is an applied Bayesian statistician. He's assistant professor of technology and operations management at INSEAD. His research explores different areas of forecasting, judgmental and statistical forecasting, modeling crowdsourced predictions, combining and evaluating predictions, and information elicitation. So welcome, Barbara and Ville.
Thank you both. Well, I'm Barb Mellers, and I'm pleased to be here. I'm speaking here today with Ville. It's a two-part talk. I'll be talking about how to improve the accuracy of human forecasts, and Ville will talk about how to understand the reasons why. I think of talks at conferences as little advertisements for papers. So we have papers that explain these ideas in great detail. So please feel free to email me or Ville if you're interested in any of the ideas that we discussed, okay? So, all right, with that, I'll begin. Every living soul that I know realizes it's very hard to predict the future. Sometimes we don't see events coming. We didn't see the Twin Towers. Most of us didn't see COVID-19. Sometimes we see the events coming, but we predict the wrong outcomes, as with WMDs in Iraq and many other examples. But for those reasons, with that in mind, the importance of predicting human forecasting correctly was picked up by IARPA, the research wing of the intelligence community, which hosted 4 geopolitical tournaments from 2011 to 2015. The goal was to study the best way to elicit and aggregate forecasts from a large, diverse crowd. So the Good Judgment team received funding and competed against 4 other teams to explore ways to help people make more accurate geopolitical forecasts. Now, the tournament lasted for 4 years, and there were over 100 questions that were asked of forecasters during that time, each year for 4 years. And they covered a wide range of topics. I'll show you in a minute. Yeah, 5 university research teams, over 500 questions, lots of forecasters, lots of forecasts. The idea of a forecasting tournament is really a great way to speed up science. What happens is that you've got a lot of people trying to solve the same problem. So all the teams had the same accuracy metric with the same questions over the same time period. And the question is, what works best? The accuracy metric was a very simple form of the Breyer score, going from 0 to 1. And this will matter later when Ville presents data. 0 is best, 1 is worst. And we constructed Breyer scores, which are sums of squares, deviations between outcomes, 0 or 1, and forecast. We computed Breyer scores over days and averaged those, and then averaged them over questions, and computed aggregate score for both forecasters and conditions to figure out what happened. I think that, let me just show you a few of the questions that we had. These were questions that were developed by the IARPA as well as the Good Judgment team, with the goal of representing things that are of interest to the IC. So I show you this because you could see the questions are all over the map. There's really no way to develop a good model that captures all of these different types of questions. Maybe some of them, but certainly not all of them. So this illustrates how important it is to work on improvements of human forecasting. Okay, so our team didn't really know how to solve this problem, so we did what came naturally, and that was to run experiments, to randomly assign people to different conditions and see what worked best. We found, well, I'm just going to tell you about 3 different drivers that influenced accuracy and proved the accuracy of the forecasters. My 3 important points are these 3 drivers plus one more big point at the end, and then Ville will take it from there. The 3 drivers that I'll discuss now are training, training forecasts to reason probabilistically, putting forecasters in teams to collaborate, and tracking, or simply identifying the best forecasters. This was defined as the top 2%, and putting them in teams to work together. I use the word tracking because this process resembles what's often done in schoolroom settings, where students of similar abilities are put in different classrooms to work together. And this is what we did with the top forecasters. So just a few data slides to show you some of the effects. Remember, lower scores are better, so you can see better Breyer scores with the forecasters who were trained than those who were untrained. We designed this training module with several goals in mind, but the main goal was to reduce cognitive and motivational biases. We explained the scoring rule. We provided tips for people about where to find data, polls, models, expert forecasts, and so forth on the internet. We discussed the importance of base rates and multiple reference classes. We talked about just 2 cognitive biases, the 2 that we thought were the most important: overconfidence and the confirmation bias. And we gave a very brief lesson on calibration and resolution. Okay, putting forecasters in teams turned out to work better than having forecasters work alone. You could see that with the yellow bar versus the blue bar. Teams consisted of about 10 to 15 forecasters, and they communicated online. Now, there's a large literature that supports the idea that independent forecasters would be more accurate than teams working together. The whole idea of the wisdom of the crowds is that you combine independent forecasts and errors cancel out in the aggregate, so forth. There's also quite a bit of literature in psychology on when and how teams can work together and benefit the aggregate work product. We had bets about which condition would be best, and I betted on one that's I'm not showing you right now, but I was completely surprised by the fact that teams did better than independent forecasters. I really had a lot of weight put on the wisdom of crowds. Okay, so we put them in teams and found that as an improvement in accuracy. And the third intervention is tracking, identifying the best forecasters and putting them together in teams. So you can see the red bar there, the super forecasters, this is 1 year's worth of data. But in this tournament, we could do replicability. We could take care of replicability problems very well. All three of these interventions worked well in each of the years that we could test them. Okay, so all right. So how accurate did we actually turn out to be? We had 2 benchmarks that were fairly good. One was the control group in the tournament. Our forecasters were 60 to 70% better than the control group. These, to show you that these interventions actually worked. And the second benchmark was pretty interesting. It was an internal prediction market that the intelligence community was conducting. And it was classified. The analysts who were participating had access to classified information. Our super forecasters turned out to be 30% more accurate than these intelligence analysts who were forecasting the same questions using the same metric over the same time period, but had additional information. That's the good news and the bad news. Okay, so this is my big point. Taken together, lots of small improvements turned out to have a very large effect on increasing the accuracy of human forecasters. You know, we often think of forecasting as a statistical problem, but I'll come back to what Bo was saying in the introduction. It's hugely interdisciplinary. The interventions that we worked on were behavioral, psychological, economic, even sociological, as well as statistical. So there's a lot of different ways to come at this. And I sort of think of it like a bit like the Model T. Henry Ford wanted to make a durable, affordable, effective car, and he introduced the Model T in 1908. Then he tinkered away at it and didn't stop until 1927, tweaking this and tweaking that and changing the production mode and so forth. And I think that's how we're gonna find out what's best with forecasts. It's a huge problem that requires so many different interventions. And I think that the psychological component is somewhat underrepresented. Okay, now my setup for Ville. All right, there's 3 ways to increase predictive accuracy: increasing information, decreasing bias, and decreasing noise. Now, we thought that our interventions would work in the following way. The probability training would reduce bias. The teaming versus independence would increase information, maybe decrease noise a little bit if team members corrected each other's errors. And tracking, well, that would probably help with everything. So the question that Ville will address is, first of all, how you can ask this question: what interventions worked and how did they work? And also give you the answer to what really happened with these hypotheses. Okay, Ville.
So thanks, Barb, a lot for that great setup. So I'm going to talk a little bit about bias, noise, and information. The rest of the talk, the way we're going to define these terms is that bias really is a systematic over or underestimation of probabilities. And then we have noise and information that are described by how the predictions actually vary from one prediction task to the next. So here we have some variability that actually correlates with the outcome. This is helpful to us, so we call it information. And then we have some variability that simply does not correlate with the outcome. This doesn't really help us to predict the outcome better. We're going to call that noise. So those are the three definitions. And with those three definitions in mind, we formulated the following three research questions. So the first thing we had in mind was, how could we actually estimate these three components, bias, information, and noise, in the Good Judgment Project data? And then can we understand what kind of roles they play in those three interventions that Barb was mentioning? That was training, teaming, and tracking. And finally, if we have a better understanding of all of that, can we use that to actually improve our interventions and make people even better at forecasting these kind of future events? So how did we do this? We introduced a new model that we call the BIN model. This stands for bias, information, and noise. So essentially, it posits a signal universe. Now, in this signal universe, there are two types of signals. So we have relevant and irrelevant signals. Now, only the relevant signals are assumed to contribute to whether the future event happens or not. And in particular, what we say is that if the sum of these relevant signals is positive, then the event happens, otherwise it doesn't. Now, you can think of this as some kind of an accumulation of evidence in favor of the event occurring versus not. So that's the signal universe. Then the way we model forecasters is that we assume that they use a sample of signals from this universe. And in particular, we assume that they have already tossed out all the signals that they know are irrelevant, so that the signals in their sample, the final sample, are all believed to be relevant. But this, of course, may not be so in reality. So they might end up actually treating some irrelevant signals as relevant. Now, this is going to create noise in their predictions. On the other hand, if they correctly treat relevant signals as relevant, this is going to increase the level of information in their predictions. And then finally, what we say is that they may center the signals or their effects incorrectly, which can then lead to this kind of a systematic bias in the predictions. That's sort of the high-level idea of the BIN model. Now, let me be a little bit more specific. For that, I need to introduce a tiny bit of notation. So in particular, first, what we have is a binary outcome that we denote with y. Now, this is equal to 0, 1, depending on whether the event happens or not. And like I said on previous slide, it is determined by the sum of the relevant signals, which under the BIN model, we model with a normal random variable that we call z star. Now, if this is positive, the event happens, otherwise it doesn't. So that's for the outcome. Now, the sum of the signals in the expert sample, we also modeled that with a random normally distributed random variable that we call z naught. Now, based on z naught, the expert then predicts that the event occurs with probability p naught. Now, in this model, we model bias, information, and noise at the level of these normally distributed random variables. And more specifically, what we say is that bias is a difference in the expected values or the means of z star and the z naught. And information, on the other hand, is covariance between these two normally distributed random variables. So intuition here is that if these two things are very strongly correlated, the expert has a good idea of what z star is based on the z naught that they actually observe, and hence they can predict the outcome quite accurately. Now, of course, there could be some variability in z naught that has nothing to do with z star, and that's what we call noise. So let me put this all together. So we have a binary outcome that is determined by the sum of the relevant signals, z star. Then we have bias. This is the expected difference between this sum and the sum of the signals in the expert's sample. We call this mu naught. The covariance between these two variables is what we call information. We denote that with gamma naught. And then the left over or remaining variability in the expert sample signals is noise, and we denote that with delta naught. The expert then predicts that the event occurs with probability p naught. Now, that would be sort of how we describe it for a single expert. And we can naturally extend this to multiple experts by assuming that each expert has their own sample that they use to make a prediction. So that's why I have denoted here Z naught with the subscript of J to denote the J forecaster. Now this gives us a group of forecasters making predictions for the future event. We call this group the control group. But now remember a couple of slides ago where I explained that one of our research goals was actually to compare two groups and understand in particular how these different kinds of intervention programs will influence the levels of bias, information, and noise. So this calls for another group, a treatment group. So how could we introduce that into this model? Now, essentially what we do is that we copy paste this control group construct, and then we just differentiate the treatment group parameters by using a subscript of 1 instead of subscript of 0. So that's what I'm gonna do. Now that gives me now a full model of two groups of forecasters and an outcome. Now here, the key assumption is that each expert makes their prediction based on their own sample of signals, but experts within the same group are assumed to have the same expected level of noise, bias, and information. Okay, so this is a model. It gives us a likelihood that we can then plug into standard statistical estimation procedures, and we can begin to estimate these parameters. So let me now illustrate to you some of the results we got when we applied this to the Good Judgment Project data. And in particular, what I want to do is that I want to consider predictions that were made 30 days before the resolution date. So this means that predictions we're going to consider were made roughly 1 month into the future. Now, as Barb was mentioning, the Good Judgment Project explored 3 interventions. So we had training, teaming, and we had tracking. Now, this table shows how each of these interventions boosted accuracy. And I know there's a lot of information here for one slide. So let me try to unpack this for you with the final column on the right. Now, in this column, we are analyzing tracking. It's the effects of tracking. And in particular, what we're doing here is that we're putting untrained individuals into the control group and then the super forecasters into our treatment group. The first 2 numbers you see are the prior scores of these 2 groups. Now remember, the lower the better. In particular, 0 would mean that it's perfect accuracy. So right away from this, you see that the treatment here improved accuracy by around 50%. Now the question is, where does that 50% come from? And that's what you see in the bottom 3 numbers. This is a breakdown of that 50% into the 3 causes, namely noise reduction, bias reduction, and we could call it better information acquisition. So what you see here in particular is that of that 50%, 23.5% came from better noise reduction, and 15% was bias reduction, and the remaining 8% came from information acquisition. So overall, what we see is that most of the boost actually derived from noise reduction. Now, we could do a similar kind of analysis or interpretation for all the different columns. And what you would discover if you did that is that noise reduction really is the key driver of good accuracy here. Okay, that's for the 30-day forecast horizon. And what about other horizons? So let's consider horizons between 1 to 60 days. In order to show the results here, I like to look at these kind of dynamic plots. Again, a lot of information. Let me just unpack this for you by using the middle column. So this one is analyzing the effects of teaming. On the y-axis, we have placed the improvement in prior score due to the training. So here, teaming. And in each point, we have decomposed that improvement in terms of noise, information, and bias, as you can see by the color-coded scheme up here. Now, on the x-axis, on the other hand, we have the time horizon. So on the previous slides, we were looking at 30-day. That will be right here in the middle. So what do we see in this figure? It shows that at long forecast horizons, so all the way here on the right, bias reduction is more important than good information. But this actually reverses as we go closer and closer to the resolution date as the forecast horizon gets smaller. But throughout, we see that noise reduction remains important. It remains consistently important. And from these kind of pictures, we can draw a very, very rough rule of thumb, which says that noise reduction is about twice as effective as bias reduction or information acquisition. So if noise reduction is so important, what can we actually do about it? What can we do to manage noise in the experts' predictions? So here are a couple of ideas. So first of all, what we could do is to try to discipline the internal judgment processes of these experts through, say, noise audits or the kind of training programs that Barb was talking about. Another idea is to collect multiple predictions and then aggregate them through different kinds of mechanisms, such as prediction markets. I believe Phil is going to tell us about prediction markets very soon, or statistical means, such as averaging. Now, we could also try to help the experts to filter through the news environment. In particular, we could try to help them to understand which signals are relevant and which ones are not. And by doing this, we can try to lighten their cognitive load. And lastly, as probably the most radical measure, we can try to replace the human judge with machine learning algorithms. Now, of course, we know that this is not always possible, like in the kind of events that Barb was talking about. And sometimes we simply need humans to make the final judgment call. It's not like we can always just hand over the reins to the machine learning algorithms. So I hope this gives you a good flavor of what the BIN model can do. Now, overall, the way I like to think about it is that it gives us a very granular understanding of how different treatments work. And this is important because with an understanding, we will be better equipped then to develop new, even more effective treatments to improve the accuracy of judgmental forecasting even further. Thank you very much. I think that's the last slide.
Yeah, thank you. So great, we have a lot of time for questions. I hope that participants can access the Q&A feature of Zoom. So please use it and submit some questions. From now on, you can submit questions throughout the talks, but we'll save them to the end probably, unless there's some clarification. Okay, maybe while we wait for the typing, I would love to hear a bit more about the effects of the training. I think you had some information on the slide, Ville. So the training that Barb talked about in terms of overconfidence, calibration, all these things, and can you measure?
Yeah, so yeah, I didn't go over it in detail, but what you can see if you kind of dig into the details of that slide is that training individuals was one of the treatments that actually did not really improve information level, or it really didn't do that much to bias either. Training really was effective almost entirely through noise reduction, whereas then teaming and tracking tended to tap into all three dimensions. And to us, this was quite interesting because we went into this thinking that bias will be the most important driver, and then noise popped out.
Great. Okay, so we have a question from Pavel. So Ville, the results you presented, can you clarify, were they at the individual level rather than, I believe, aggregated teams would be the alternative?
Yeah, no, that's a good question. So we did not do the analysis within teams. We actually did it at the individual level. So let me just clarify this question a little bit, because I think I know what he means. So what happened is that in the data, there were a lot of different teams. So I think what Pavel is asking is that did we actually do the analysis within each team separately? No, instead what we did was that we used all the individuals together in one big pool of this intervention where they were allowed to talk within their own team members.
Great, thanks. So Rajiv asks, it looked like in one of the figures, their bias reduction went negative. Can you tell us about that?
Yeah, no, that, Barb, do you want to talk about this?
Sure, I'll talk about that.
Yeah.
This is really great. What happens with the super forecasters is that about 10 days before the question is scheduled to close, they start getting, you know, these guys really want to win, and they start getting a little cocky. and
Okay.
they sort of start increasing their forecast typically to be higher and higher and higher because they think it's so likely to happen, but sometimes they overstep their bounds and the event doesn't occur or something unusual happens right before. And so that's the bias that we see. It's serious, it's real. And we think it's a function of the way in which we set up the incentives. Perhaps we could change it. But yeah, we thought that was wild, and it actually is correct.
Sorry, can you help me understand what does it mean when the bias reduction is negative?
The bias is set up. We recoded all the questions such that the bias means you overpredict the likelihood of the event, and that's exactly what they were doing, over predicting events. Sometimes events didn't occur. And so that was the systematic deviation. And that's because they juggle their forecasts at the end and try to, maximize their buyer scores and shoot it up to higher amounts in this case in order to get a better score.
Thank you. We have a new question from Yichi. Let's see. So I recall that one result is that using the 3% experts will greatly benefit the aggregated forecast's accuracy. Is this 3% level optimized? And are there any insights on why using this number? And maybe you could give us a background of what the 3% experts means for the rest of us.
Let me try to clarify the question. Using the 3% experts, do you mean the 3% or 2%, the super forecasters?
I think the super forecasters is what's meant, yeah.
Greatly improve the accuracy of everybody? Is that the question, or the super forecaster?
I think the question is getting at how do you draw that threshold before someone's a super forecaster who goes into the aggregation and the others are kicked out?
Yeah, it's totally arbitrary, completely arbitrary. And we did it for a variety of unrelated reasons that had to do with managing this whole tournament. We could have called super forecasters the top 20%, made a lot of people happier. But I think that's a bigger, perhaps institutional or organizational question rather than a theoretical one in any sense.
But so I guess we could go back in hindsight, and there might be sort of overfitting type problems, but we could just try to see, at what level does adding people actually reduce the accuracy, the Breyer scores or something? I'm curious if there is some analysis.
In terms of how many forecasters?
Like sort of the optimal subset. If we just sort of went back and tried to find the optimal subset of forecasters whose aggregated forecast, was the most accurate, would we take the top 2%? Would we take the top 20?
Yeah, right. Well, it's interesting. One of the things we didn't talk about is the effects of the aggregation rule that we used. There was one rule that turned out to be the best each year for 4 years in the tournament. And it's relatively simple. Ville and Lyle Ungar developed it. Basically, I can give you the less complicated version. First thing we did was to discount forecasts that were further away in time. And that means we're focused on the most recent ones. And if super forecasters are updating a lot, which they did, we'll have a healthy dose of super forecaster input in there. Next thing we did was to weight people based on previous accuracy. We computed an average, and then we extremized it, which is to say, we acted as if the aggregate had more information than it really did. So if the weighted average was 0.3, the extremization would make it 0.1. And if it was 0.7, it'd push it out to 0.9. And that's a really interesting, wonderful story that Villa has written some lovely papers about. So do you want to add anything, Villa?
No, I wanted to add also that, I'm not muted, good. Another sort of a follow-up paper we did to what we presented here today is one where we treated the treatment as an aggregation. So in some sense, what we did in that paper, we said that, look, you have individuals forecasting, that's our control group. Now let's consider a treatment group with only one prediction, which could be a different type of aggregate of those control group individual forecasts. And that's where we applied bin model to try to understand how various different kinds of aggregators actually come about the wisdom of the crowd effect. So we consider prediction markets, we consider different types of averaging like techniques. And there, in particular, we applied also to the different groups of forecasters that we see here. And in particular, what I find interesting is that for the super forecasters, averaging is really the best thing you can do there. I think it's probably because they are all really pushing the limits of the information that is out there. And a lot of the disagreement they have tend to be driven by noise, and averaging is just a wonderful way to eliminate that noise. So this is something we also discovered there.